All right, everybody, welcome back for another deep dive. Today, we're strapping ourselves in for some serious spinning. We're talking about circular motion.
That's right.
And, I was looking over these physics class notes on circular motion, and I have to admit, I was getting a little bit lost. So I figured, hey, why not bring in the expert to help break it down for us? I'm sure a lot of you out there have felt that same sense of, wait, what force is doing what now when thinking about circular motion? It can be a little mind-bending.
Yeah, I get that. It definitely can be.
So we're going to try to untangle all those forces today. From the crazy carnival rides that make you scream to the planets calmly orbiting the sun, we're going to figure out what's making the world go round. Well, actually spin round.
I like it.
These notes start off by talking about uniform circular motion.
Okay.
And at first glance, it seems simple enough. Something's moving in a perfect circle at a steady speed.
Right.
But then they hit you with this, it's still accelerating, and I'm like, hold on a second. If the speed isn't changing, how can it be accelerating?
That's a really good question, and it trips a lot of people up. You have to remember that acceleration isn't just about going faster. It's about any change in velocity. And velocity includes both speed, how fast you're going, and direction, which way you're going. So even though the speed stays the same in uniform circular motion, the direction is constantly changing as that object whips around the circle, meaning, yep, you guessed it, it's constantly accelerating.
So basically, it's the change in direction that's the key here, not necessarily the speed.
Exactly. And there's something even cooler about this whole acceleration thing. The force that's causing that acceleration and the acceleration itself are always pointed towards the center of the circle. That's the force that keeps the object from just shooting off in a straight line. It's like an invisible string, constantly tugging it back towards the center. And that force, my friend, has a name. The centripetal force.
Okay, that makes sense. But then how come when I'm on one of those spinning rides, I feel like I'm being flung outwards? If everything's being pulled inward, why does it feel like I'm going to fly off into space?
You know, it's almost like our brains are playing a little trick on us. It's not so much about a force pushing you out, but more about your body's natural instinct to resist any change in motion. That's inertia. You see, your body wants to keep moving in a straight line, like it was before the spinning started. But that centripetal force keeps yanking you back toward the center, forcing you into that circular path. And so your body's resistance to that change in motion makes you feel a sort of outward push. And we often call this centrifugal force. But it's not really a true force. It's more like an illusion.
Oh, I see. So kind of like when you're in a car that takes a sharp turn and you feel pushed against the car door. It's not really a force pushing you. It's your body just wanting to keep going straight.
Exactly. That's inertia doing its thing. It tricks you into thinking there's a force pushing you outwards when it's really your own body's resistance to change.
Okay. Illusion busted.
Mm-hmm.
So these notes also dive into something called tangential velocity. Can you tell us more about that?
Absolutely. So picture this. You're on a merry-go-round, way out on the edge, and your friend is closer to the center. You're both going around in the same amount of time, making a full circle together.
Right.
But you're actually moving faster than your friend, even though you're both completing the circle simultaneously.
Interesting.
That's because you're covering more distance. The farther out you are on the merry-go-round, the bigger the circle you're tracing. And so the faster you have to go to complete it in the same time as someone closer to the center. And that speed along the edge of that circle, that's your tangential velocity.
So that's why the outer edge of a spinning ride always feels so much more intense. You're actually moving faster.
Exactly. The thrill comes from that higher tangential velocity. Now, how do you think gravity ties into all of this circular motion?
Well, that's a good question. I know it keeps me planted on the ground.
It does, but it's also the unseen force behind much of the circular motion we see out in space. You see, gravity is what keeps those planets spinning around the sun and moons around their planets. Imagine it like this. Gravity's pull creates a kind of dip in space, like a cosmic dent. And the planets, they get caught in that dip, constantly falling toward the sun because of gravity's pull. But they're also moving forward. And this combination of falling and moving forward creates that continuous circular path, like a cosmic dance.
So gravity isn't just pulling us down to Earth. It's orchestrating these grand cosmic waltzes throughout the universe. That's incredible.
It is pretty amazing.
Could you tell me more about this gravitational force and how it works?
Of course. So imagine the universe is like a massive playground with objects of all sizes scattered about. Each of these objects, from the tiniest speck of dust to the largest star, has something called mass, which you can think of like the amount of stuff in it.
Okay.
And here's the thing. Every single object with mass is constantly pulling on every other object with mass. This invisible pulling force, that's gravity.
Wow. So everything is pulling on everything else.
That's right. And the strength of this pull, it depends on two things: how much mass each object has and how far apart they are. The more massive an object is, the stronger its gravitational pull.
Makes sense.
But the farther away two objects are, the weaker that pull gets. It's like a magnet. The closer you are, the stronger it sticks.
So that's why we'd weigh less on the moon than on Earth.
Exactly. The moon is much less massive than the Earth, so its gravitational pull is weaker. It's like a gentler tug compared to the Earth's firm grasp.
This is all starting to make a lot more sense now. We've got the centripetal force keeping things moving in those perfect circles. Inertia making us feel like we're being pushed out when we're really just resisting change. And then, of course, there's gravity orchestrating those celestial ballets, keeping the planets and moons in their orbits. What a fascinating interplay of forces.
It really is. And the best part is, this is just the tip of the iceberg. There's so much more to learn about these forces, about their applications, and about how they shape the world around us.
It's really mind-blowing when you think about how all these invisible forces are constantly at play. And it's a great reminder that there's always more to learn, more to explore. So next time you see a spinning object, whether it's a spinning top, a swirling storm, or even just the tires on your car, take a moment to appreciate those invisible forces that are making it happen. Keep that curiosity spinning.
That's the key. Keep exploring, keep asking questions, and who knows what other mysteries you'll uncover. There's a whole universe of wonder out there.
Thanks for listening, everyone, and we'll catch you next time for another deep dive.
See ya.